Hi, I am Saurabh Yadav. I'll be presenting our work on complex valued neural networks titled Fully Complex Valued Convolutional Networks using Complex Valued Color Model and Loss Function. First, let's see what a complex valued neural network is. In layman terms, we can say that a complex valued network has complex valued weights instead of real values. There are a wide variety of works that showcase the usefulness of complex valued neural networks. Some show that these networks are better for object-centric learning, while some show uses in applications such as depth estimation and multitask learning. Now let's focus on these networks in vision domain. Using complex numbers, we can have a better representation of features. We also see that these networks are really useful in areas where complex valued input is inherently available. Earlier work showed that in image classification we get comparable results to real valued networks. Now let's see what are the problems from previous works that we can resolve to improve these networks. First, let's focus on input. In typical setting, the input is real valued. Even if we consider the input as real component of a complex input, the imaginary component is 0, providing no information. Second, when we take that input to the network, the complex information is only carried till convolutional block and then it's converted to real value by various methods as shown in previous works. Third, if we continue the complex valued information till the end, we need to have a loss function that caters specifically to complex valued output. Here is an overview of our proposed contribution to solve these problems. Now let's discuss them in detail. First, let's try to obtain a complex valued input. Previous work simply used different color encodings to create a complex representation of images. We propose to define our own complex valued color model IHSV inspired from HSV color model to obtain complex images. As we know, HSV color space is represented using a cylinder where HSV represent 3 dimensions: hue, saturation, and value. If we keep each dimension constant at a time, we can obtain 3 different Argand planes. So each pixel P in HSV color space can be located in these 3 Argand planes. Let's see how. In first case, when we keep hue constant, we obtain a 2D Argand plane where value, saturation are variable. Value represents real axis and saturation represents imaginary axis of the Argand plane. So the pixel P in this plane can be represented as IV plus IIS. In second case, when we keep saturation constant, the HSV cylinder gives only a hollow cylinder. Upon opening it, we can get a 2D plane where pixel P can be located using arc length IS into variable hue and variable value. So the pixel in this Argand plane can be located as IS into IH plus IIV. In third case, upon keeping the value constant, we only obtain a circular plane. Pixel P in this plane can be located using polar coordinates with variable hue serving as angle and variable saturation serving as magnitude. So finally, we obtain our third complex number using IS cos IH plus IS sin IH. Here is the proposed algorithm for converting real valued input images to complex valued images using our complex valued color model IHSV. Here is also a table representing pixel values of some of the common colors. Here is a flowchart of how real and imaginary component is formed. Next, moving on to our second problem, loss of complex valued representation after convolutional block. Unlike previous work, we want to preserve that information. To do that, we propose to use existing complex convolutional operation to continue handling complex valued features. We propose to replace fully connected layers with 1x1 complex convolutional layers. Here is a block diagram of the process described before. Now we can obtain a complex valued output at the end, but we have another problem. That is, we don't have a loss function to handle complex output. Let's try to define a complex loss function. Considering a function fcomp that takes complex input and gives complex output, we can obtain a complex output z from input sample x. Let's put our complex output z in cross entropy loss. But when we expand z into its magnitude and phase, we obtain a modified version of loss function. Here, real component of the loss caters to magnitude, which represents predicted probabilities of classes, and imaginary component caters to the phase of the output. We also need to ensure that complex valued loss is indeed differentiable for backpropagation. To show that complex number function f is differentiable, we need to show that it follows Cauchy-Riemann conditions. If we prove log z, where z is a complex number, is differentiable, then our loss function is also differentiable. When we do that, we see that log z follows the condition. Thus, by extension, our proposed loss function is differentiable too. Here are the results from our conducted experiments. We compare the results of 5 different inputs on 5 different datasets, showing better results for FCCN. We also compare with previous methods on large-scale dataset and models in Table 4, and on complex valued dataset in Table 5, where we see better accuracies for FCCN. We also do 3 different ablation studies. In Table 6, we observe the effect of color channels in complex input. In Table 7, we compare the effect of each contribution. And lastly, in Table 8, we observe improvement across various datasets. Thank you.